Hello all, this is Valentino and this is another video where we will go over a past paper, and this one is Unit 1 from January 2025 from the International A-Level series by Edexcel. And as I have been doing recently, we will just dive in and then I will tell you things about the paper as we go. Okay, so let's start with section A, question 1. So stress is applied to a sample of a material. The stress is increased until the sample breaks. The graph shows the relationship between stress and strain for the sample. Okay, which of the following gives the Young modulus of the material? So this one is kind of easy. Recall that the stress is equal to the strain times the Young modulus, right? So if we plot if we make a plot of stress versus strain, right, the gradient is going to be the Young's modulus. So, but let's read the options. Option A, the area between the line and the strain axis. B, the gradient of the graph. That's the correct answer. C, the maximum stress multiplied by the maximum strain. That's totally wrong. And D, the maximum strain divided by the maximum stress. Okay, so here comes my first tip for past papers by Edexcel. In the multiple choice section, it is often the case, just right in this case, when we can eliminate 3 out of the 4 answers, okay, or sometimes 2 out of the 4, which means that you are left with 2 choices, okay. But here, all the answers are totally wrong because the area between the line and the strain axis represents something else, as we will see later, I think, in this test. And option C and D are totally wrong, okay? So let's move on to question number 2. A coin and a feather are dropped from the same height through air, okay? So that's the key there, okay? Because if it was through vacuum, they will fall at the same time. So anyway, which row of the table is correct as the coin and the feather fall to the ground? Okay, so the initial acceleration should be the same, right, for both objects. So options A and B are erroneously wrong, okay? And the acceleration is the same because it's g, right? It's in the gravitational field of the Earth. And then the time taken to reach the ground will be less for the coin, right? Because the air resistance is almost insignificant for a heavier object like that. So C is the correct answer. Okay, so you see how this is another example actually where we can eliminate 2 out of the 4 answers immediately, and then you can eliminate option D as well, okay? So yeah, so you can arrive at the correct answer by eliminating all the wrong answers. Another tip, multiple choice questions award 1 mark, so they should take you about a minute, okay? And this is a general rule for these tests, the unit 1 through 6 tests. If a question awards 10 marks, it should take you 10 minutes. If it awards 5 marks, about 5 minutes, etc. So this way will help you to track the time so you score the maximum possible marks. Okay, question 3. A physical quantity can be either a scalar or a vector. Which row of the table is correct for acceleration and work done? Okay, we know that acceleration is a vector, so options A and B are wrong. And then we know that work done is energy, right? So it's a scalar. Energy doesn't have a direction, right? So C is the correct answer. Again, this is another example, the third in a row, in which 3 out of the 4 answers are wrong. Question 4. A spring is stretched beyond its elastic limit. The applied force is then removed. Which of the following describes the behavior of the spring? Okay, option A, the extension of the spring is always proportional to the force applied. This is relevant to the question. B, plastic deformation occurs until the spring reaches its elastic limit. That's wrong. Doesn't make any sense, actually. C, the spring only shows elastic deformation. That's wrong because we go beyond the limit of beyond the elastic limit. And then D, the spring does not return to its original length, which is the correct answer, because beyond the elastic limit we get plastic deformation So the extension, any extension of the spring is permanent. Okay. 5. An aeroplane lands on a runway at time 0 and then decelerates. The graph shows how the deceleration of the airplane varies with time. Which of the following does the shaded area on the graph represent? So option A, the displacement of the airplane at time t, that's wrong, okay? Actually, I mean, it's really simple. So if you multiply acceleration with time, which is what's represented by this area there, right? Okay, it's a trapezium, so it will be 1/2 times base times height over 2, something like that. So, but acceleration times time has units of meters per second squared times seconds. So it has units of velocity, okay? So B is also wrong, the change in displacement. It's not displacement, okay? C, the velocity of the airplane at time t, that's also wrong, okay? Because the area under an acceleration or acceleration time graph always shows the change in velocity of an object, and here it's the airplane, so D is the correct answer. Again, another example where we can eliminate all wrong answers to find the correct one. And I have videos, by the way, about these concepts, so you can go check the video where I talk about these types of graphs. Okay, check my channel. Okay, 6. When a force F is applied to a spring of stiffness K, the extension of the spring is delta X. A force 2F is applied to a second spring of stiffness 3K. Which of the following expressions gives the extension of the second spring? So, okay, for the first spring, we have a force F, which is equal to K times the extension. So the extension is F over K. Okay, for the second spring, we have a force of 2F and a spring constant of 3K. And let's call delta X prime the extension. So delta X prime is 2/3 F over K, which is 2/3 delta X, the one we found in the beginning. Okay, so that's option A, right? Yes. Okay. 7. A student drops a ball and measures the time taken for the ball to reach the ground. He repeats this for different heights. He uses, a graphical method to determine a value of g, the acceleration of free fall. He plots height on the y-axis of the graph. Which row of the table is correct for the student's graph? Okay, let's go do some calculations. So I'm going to use a clean page. So this is a scenario in which we can use this Suvat equation. So actually, let's call it S to begin with, and then I will show you. So S is U times T plus 1/2 AT squared. For this case, for the student's case, S is Y, the height, U, the initial velocity is 0, and Y is 1/2 GT squared. Right? So if we plot y versus t squared, we will get a straight line with gradient g over 2. You can also plot 2y versus t squared, and in that case, the gradient will be g, but let's go see what the options are. So quantity plotted on the x-axis, time, then the gradient of the graph will be 1 over g. That's not supported by this equation, because if we plot t on the y-axis, then we will have a relationship of the form t is the square root of 2y over g, so that doesn't work, okay? Same with b, it doesn't work. Then option C says that if we plot t squared on the x, quantity on the x-axis is t squared, so that's the x-axis, right? Then the gradient of the graph will be g over 2, that's correct actually, okay? And then D repeats the same information, so time squared on the x-axis, but the gradient is 2g, which is wrong, okay? So for 7C is the correct answer. Okay, question 8. The velocity time graph for a train journey is shown. Which of the following expressions gives the distance traveled by the train in time to t? So delta S is going to be the area under the curve. Okay, so it's going to be this area. Okay, so the area is going to be, we can split this into two. So let me erase this actually. Okay, so we can split it into this rectangle 1 and then this triangle number 2. Okay, so the area is going to be V times 2t. That's the area of the rectangle, area 1, plus 1/2 the height, which is between 2v and v, that's v, right? V times t, and that's the area of that's area 2. Okay, so we get 5/2vt, which is d. Okay, question 9. A free body diagram, a free body force diagram for an object moving through a fluid is shown. Okay, we have the upthrust, the drag, and the weight. The mass of the object is 5 kilograms. The object is accelerating upwards at 4 meters per second squared. Which of the following gives the magnitude of the drag force in newtons? Okay, so the motion is up, so upthrust is positive. So we can use sum of all forces is ma, and a is again upwards. So upthrust is positive minus drag minus weight is equal to ma. We are interested in the drag, right? So drag is upthrust minus weight minus mass times acceleration. So 90 minus 49 minus 5 kilograms minus times 4. So that's option C, right? Okay, and so the final question in in section A. 10 traffic lights of weight W are suspended from a wire. The wire is held at an angle theta to the horizontal by 2 supports as shown. Which of the following expressions gives the tension in the wire? Okay, we need to do some geometry now. Okay, so let's design this straight line. So by Thales principle, that angle is theta, that angle is theta as well. Okay, the weight, let's draw it like that. That's the weight. And then we have the tension, let's do green. So that's the tension from the first support and the second support. We can analyze the tension into a horizontal component, which is going to be t cosine theta for both cases, right? So these two cancel pretty much, right? And then we will have 2 times t sine theta, because we will get a contribution from this force and another one from this force 2 times. So 2 times sine theta. So 2 times t times sine theta is equal to the weight. So what do we need to find? The tension. So tension is weight over 2 sine theta. Sorry guys, I'm a theoretical physicist. Sometimes I get distracted. So I actually forgot what we were trying to find. So that's, okay, so option B works. Okay, so this was section A. Straightforward. Again, 2 tips. The first tip is that it is often the case when you can eliminate 3 out of the 4 answers. Most of the times you can eliminate 2 out of the 4 answers. Okay, so that makes your life easier. And the second tip, which applies to all the tests, is guys, read the questions thoroughly, make sure you understand what they are asking you to find. And as I say, half the answer is in the question. Okay, so if you don't understand the question, it's really hard to solve the problem. All right, so let's move to part B, section B. Okay, question 11. The mass of a car is 1,850 kilograms. Some people sit in the car then accelerates at 0.23 meters per second squared when the resultant force on the car is 460 newtons. Calculate the total mass of the people in the car. Okay, so the resultant force is going to be equal to the mass of the car plus, let's call it M, the mass of the people, capital M. So mass of people, we denote it like that, times the acceleration. Okay, so M plus M is sigma F over A, right? So the mass of the people is going to be sigma F over A minus the mass of the car, which is 460 over 0.23 minus 1850, which yields 150 kilograms. Okay, this was straightforward. So let's move on to the second question in section D. So question 12. Okay, next question is 12. A person on skis slides down a slope. The slope is at an angle of 14 degrees to the horizontal. The initial speed of the person is 7.1 meters per second as shown. The resistive forces acting on the person are negligible. Calculate the speed of the person after moving 15 meters down the slope. Okay, so for this question, we actually need to find the acceleration, so we can use Suvat equations to find the final speed. So how are we gonna go about finding the acceleration? We need to find the sum of all forces acting on the skier in the direction along the slope. So let's go do that. So the only force actually the weight, which points down, and okay, yeah, and the reaction, excuse me, from the slope n. Okay, so that's n. All right, so we can analyze into a component that is along the motion and a vertical component. Okay, so the way I always explain how to find the angle. So this side is perpendicular to this side. Okay, and now this side, sorry, is perpendicular to this side. The inscribed angle is 14, therefore this angle is 14 as well. Okay, let me remove the lines. So this angle is 14 degrees, and we have the component of the force of the weight along the perpendicular direction, which is W cosine 14 degrees, and a component W sine 14, which is the one that causes the acceleration since it's not balanced by anything, right? So we can use sigma F is equal to ma along the slope to find the acceleration. So mg times sine of 14 degrees is ma. Okay, so m cancels. So a is g sine 14 degrees, and we want to find the speed after the person moved 15 meters down the slope. The best Suvat equation for that is v squared equal to u squared plus 2as, since we know the initial velocity, the acceleration, and the distance covered. Okay, so we are just gonna plug in values. So we have 7.1 squared plus 2 times g times sine 14 degrees, and this is our acceleration, right? Times the distance covered, which is 15, and this yields 121.6. So we need to take the square root. So v is 11.03, which is about 11 meters per second, which is the answer. Okay, straightforward, I believe. Okay, but as far as you choose the correct Suvat equation, okay, because that simplifies this problem enormously. Okay, let's move on to the next question. Question 13. An escape lane can stop cars or trucks safely if the brakes stop working when moving downhill. The photograph shows an escape lane. For the record, there are actually 2 escape lanes like this near where I live, and I believe they are the only ones in Cyprus for some reason. Okay, yeah, I live in a very hilly region, but I tried to remember, to recall, but I think I've never seen these escape lanes anywhere else in Cyprus for some strange reason. Anyway, so the escape lane is made of sand and is horizontal as shown below. The resistive force of the sand on a vehicle reduces the kinetic energy of the vehicle. Question A, as a truck enters the escape lane, the kinetic energy of the truck is 8 times 10 to the 6 joules. The sun exerts an average resistive force of 3.45 times 10 to the 5 newtons on the truck as the truck comes to rest. Calculate the distance moved by the truck on the escape lane. Okay, so the idea is that all kinetic energy, okay, has to be consumed. I'm going to write it like this in quotes. So it has to be consumed by the work done, okay, by the resistive forces. Okay, so let's create a clean page and write that the work done by the resistive forces should be equal to the kinetic energy, right? But the work done is equal to the force times the distance, okay? And this should be equal to the kinetic energy, okay? So the distance covered is equal to the kinetic energy over the force. So that's 8 times 10 to the 6 over 3.5 times 10 to the 5. The units are newtons times meters for the kinetic energy and newtons for the forces. Newtons, by the way, newtons times meters. This expression gives you the joule, okay? All right, so if we perform the calculation and find 22.83 meters, maybe we can write it as 22.8 meters or even 23 meters. Okay, moving on. Part B, the resistive force exerted by the sand on a vehicle, is proportional to the weight of the vehicle. The weight of a car is less than the weight of a truck. Explain how the deceleration of a car on the escape lane would compare with the deceleration of a truck. So they are telling us that the resistive force is equal to some constant K times M times G, right? We can write this. We can write this since F is proportional, let's write it like this, to M times G, okay? But the sum of all forces should equal MA. So the resistive forces KMG is equal to MA. So A is simply K times G. So it's independent of the mass, okay? So since M cancels, okay, the acceleration is proportional to K and does not depend on the mass of the vehicle, right? So the acceleration, actually deceleration, so the deceleration is the same. Okay, so you would expect, something else, a different result, but actually it doesn't matter. I mean, the deceleration does not depend on mass, as we just showed. Okay, moving on. Okay, question 14. An air track is a straight tube with holes along its length. Air forced through the holes lifts the gliders, preventing friction between the gliders and the air track. A teacher uses an air track and two gliders A and B to demonstrate the principle of conservation of linear momentum. Gliders A and B move towards each other and then collide. Question A, state how Newton's third law applies to the gliders during the collision. For the record, when I was doing my PhD in the United States, one of the first assignments I had was a teaching assistantship, which means that I was helping with lab teaching and tutorials and stuff like that. But anyhow, one of the first experiments I did was with the students was this one with the air track. So I'm very familiar with that. So anyway, State how Newton's third law applies. Okay, so A exerts a force on B, okay, during the collision, and B exerts an equal in magnitude, okay, and opposite in direction force on A. Okay, so these two forces act on different objects, hence they constitute a Newton's third law pair. Okay, so at the moment of collision, pretty much we have this is A and B. So this is the force that A exerts on B, and there's another force to the left by object B on A. Okay, I hope this makes sense. And the two are equal and opposite, so they cancel. So the sum of all forces during a collision is 0, so momentum is conserved, right? So let's go back and do part B. Gliders A and B have different masses and move at different velocities before the collision is shown. The gliders stick together, in the collision. A student predicts that the gliders will move to the left, okay, after the collision. Deduce whether the prediction is correct. So we can split the situation to before and after. Okay, so after we will assume that you have these two masses stick together, and let's assume that they move to the right. Okay, if we get a negative sign, it means, that the two objects move to the left. Okay, the initial momentum is 0.15 times 0.32 minus, because the minus sign for glider B comes from the fact that it moves to the left. Okay, so minus 0.2 times 0.11, and this yields 0.0249 kilograms meters per second. Okay, so immediately see that they have to move to the right because it had to be negative, right? But anyway, the final momentum is going to be 0.2 plus 0.15 times final velocity that we denote by v. Okay, so this is equal to 0.35 v. Pi should be equal to pf, so 0.35 v is 0.0249, so v is 0.07 meters per second to the right, so student is wrong. Okay, I think it's a straightforward application, so I don't have anything else to add here. So let's move on to the next question. Okay, question 15. I don't know how that's pronounced, so forgive me. The Croatian, maybe? Croahan? I don't know. Let me know in the comments. I don't know what the pronunciation is. So this hydroelectric power station in Scotland is built inside a mountain. This sounds really interesting. If you guys have seen this before, I mean, if you visited it, let me know in the comments. So water from a lake near the top of the mountain flows through straight pipes to a generator. The pipes have a length of 350 meters and are inclined at an angle of 55 degrees to the horizontal as shown. The gravitational potential energy of the water in the lake is used to generate electrical power. In 1 minute, each pipe transfers 1700 cubic meters of water to the generator. The density of the water in the lake is 1100 kilograms per cubic meter. Show that the power transferred by the water in each pipe is about 88 megawatts. Okay, so first of all, let's find the GP, the gravitational potential energy of the water, and we will do so using okay, it's MGH, right? but we don't know the mass of the water. We know the density, and we know how much volume per minute is transferred. So rho times V gives us the mass times G times H. We don't know H, but we know the hypotenuse of this triangle. So H is going to be this height that I'm drawing right now with blue. So that's H. So we can see that that can be calculated using sine of 55 is H over the hypotenuse, which is 350. So H is 350 times sine of 55 degrees. And in fact, we are not given the volume per se, we are given the volume per minute. Okay, so if we divide the GP by time and the volume by time, we get a quantity that has units of joules per second, which is watts. Okay, so that's the quantity we actually need. I hope this makes sense. Okay, so so the energy, let's call it E, is going to be the GP per time. So rho, let's plug in numbers. The density is 1100, right? And that's kilograms per cubic meter. Volume per time is 1700 cubic meters. And per 60 seconds, okay, we convert the minute. 1 minute is 60 seconds times 9.81. That's meters per second squared. And then times 350. That's meters. I'm sorry if it's confusing. Times sine of 55 degrees. Okay, I crammed everything there. I'm sorry. So we get many cancellations. Let me see. So cubic meters and cubic meters cancel. And we are left with kilograms times meter squared over second squared. So this over here, so these units over here create a joule, and joules per second is a watt. Okay, I hope this is clear. So we get 87.7 times 10 to the 6 joules per second, which is about 88 megawatts. Okay, so that's the answer, which matches what they are asking. So let's move on to part B. Water travels from the lake to the generator through 4 identical pipes. As water moves through the 4 pipes to the generator, the total power wasted is 256 megawatts. Calculate the efficiency of the power station. Okay, so the input is 4 pipes times 87.7 megawatts, right? So that's the energy available, so 350.8 megawatts. Okay, the useful energy is equal to the input minus the loss. So that's 350.8 minus 256 due to the loss. So the useful energy we get out is just 94.8 megawatts. So there is a lot of loss, in other words. Okay, so the efficiency is given by the useful energy we get out over the input times 100. So that's 94.8 over 350.8 times 100, which yields 27%. Okay, so this was question 15. Let's move on to the next question. Okay, question 16. A balance is formed, by a beam suspended from a string. A dish is hung from the beam, and the balance is used to measure a fixed portion of rice. When the dish contains one portion of rice, the balance is in equilibrium as shown. Question A, state the conditions needed for an object to be in equilibrium. I'm gonna write this laconically, which means very shortly. Okay, so the sum of all forces should be 0, and the sum of all moments should be 0. Okay, and the moments about any point. Okay, Part B, and you can see, by the way, that's another thing I forgot to mention. So this is 6 marks, and as I said before, it should take you about 6 minutes. But this also indicates that this is the hard part of this question, because the previous part is just 2 marks. Okay, part B, the dish is moved along the beam so that the horizontal distance from the string to the dish is 7 centimeters. Rice is added to the dish until the balance is in equilibrium. Deduce whether the dish now contains 3 portions of rice. You should include a calculation for the weight of 1 portion of rice, and they give you the weight of the beam and the weight of the empty dish. So for 1 portion, we were told in part A, so here in the description of the problem, that's 1 portion of rice, okay, so of rice. I don't know what I'm saying today. So we have to use the principle of moments about this string. Why about that string? Because there are 3 forces actually acting on the beam. So the weight of the beam, the weight of the portion of the rice plus the disk, and then the reaction, the tension from the string. Okay, so we take moments about the point, about the string, so we get rid of that force. Okay, so we have let's go see what's going on here. So we have 8 centimeters, right? So 8 centimeters times the weight of the beam, so 3.1, should be equal to the weight of the portion plus the weight of the disk times 25. Okay, so I'm gonna do this a little bit fast. So the weight of 1 portion is 0.35 newtons. Okay, from the beginning, I mean from the wording of the problem. Now they tell us that the dish is moved along the beam so that the horizontal distance from the string is 7 centimeters. Rice is added, and we have equilibrium again. So for the second scenario, okay, I'm going to draw a line to separate the second scenario. So in the new position, we still take moments about this point, okay, about the string. So in the new position, we have 8 centimeters times the weight of the balance, the weight of the beam, which is 3.1, is equal to some constant n, let's say, times the weight of 1 portion plus 0.64, which is the weight of the empty dish, times the new distance, which is 7. Okay, so actually, okay, n times the weight of 1 portion, we can immediately write n times 0.35, okay, which is the weight of 1 portion. I hope you guys understand what I'm doing, okay? So n times 0.35 is equal to 2.9. So n is 8.25 portions, so not 3. Okay, way more actually. Okay, let's move on to the next question. 17. A tugboat is a small boat that can be used to pull large ships. A tugboat is attached to a ship using a thick rope. A sample of the rope is tested to make sure that the rope will not break when a ship is pulled. Question A. The original length of the sample was 36.8 meters. Calculate the strain in the sample when the length of the sample increased to 38.1 meters. Okay, so delta x is going to be 38.1 minus 36.8, which is the original length, so 1.3 meters. So the strain is delta x over L, which is 1.3 over 36.8, the original length, the extension divided by the original length, so 0.035 is the strain. Okay, part B, the stress strain graph for the sample is shown. Okay, beautiful. Question I, the diameter of the sample is 220 millimeters. Determine the force applied to the sample when the strain was 0.025. Okay, so let me think. So 0.025 is this point over here. Okay, so we can see from the graph, okay, so that's 0.025 because how do we know this? Because between here and here we have 0.01, an increment of 0.01. Therefore, the midpoint is 0.005 or 0.025. Okay, and in the vertical direction, every small increment, so every small square is an increment of 5. So we have 2 squares there, so 110 megapascals is the stress. So stress is force per cross-sectional area. So force is strain times the cross-sectional area, which you can write as pi d squared over 4. So we have 110 times 10 to the 6 megapascals, which is newtons per meter squared, times pi times the diameter, which is 220 times 10 to the negative 3 squared, and that's meters squared, over 4. So that's 4.18 times 10 to the 6 newtons, which you can write as 4.2 times 10 to the 6 newtons. Part 2, explain how the area under the stress-strain graph and the volume of the sample can be used to determine the energy stored. So the area is proportional, so let's write it like this, to sigma times strain. Okay, we can write, yeah, okay, let's keep it like that. So, but what kind of dimensions, what kind of units does stress times strain have? So let's go see. Stress times strain can be written as force per cross-sectional area times the extension over the original length. But okay, in the case of the rope, right, notice that this is going to be A, and that's the length, right? So A times length is the volume, right? I hope this makes sense. And also notice that F times delta X is the definition of the work done, right? So that's energy, okay? So we have energy per volume, okay? And that's the answer. Wait, that's not the answer. Explain how the area under the stress-strain graph and the volume of the sample can be used to determine the energy stored. Okay, so we can then write that the area is energy over volume. Therefore, area times volume is the energy stored in the sample. Okay, that's the answer. And let's move on. I think I discussed this. If you go watch my video on stress strain, I think it's called, search my channel and you will find it. I think I discussed this. So let's move on. 18, a small remotely controlled submarine is used to explore the sea. The way this wording reminds me of something that I shouldn't be commenting on a video that is watched by high schoolers, but the cartels, I think, in South America do use submarines for their operations, okay? Please verify the information, though, because I read it once and I never really researched it deeper to figure out whether they are actually building their own submarines. So anyway, and it also reminds me of the Yellow Submarine by the Beatles. So question A, the engine of the submarine produced a horizontal force of 70 newtons. The drag force on the submarine was 43 newtons at an angle of 25 degrees to the horizontal as shown. Determine the resultant of these two forces on the submarine by drawing a scaled vector diagram in the space below. Okay, this means that I have to bring up the ruler, and those of you who are watching my videos know that I actually don't like these graphical methods, but okay, we have to do it. So 1 centimeter denotes 10 newtons. Okay, So let's start from 0. So 70 newtons, okay, good. So that's the force from the engine, so 70 newtons. And then 43 newtons have to be 4.3 newtons. And then the angle of 25 degrees, you see that the ruler has degrees. But if I go this way to the right, it starts reducing from 180. So 25 degrees is actually 180 minus 25. So 155 degrees will do. So let's turn this to 155. Okay, there you go. Okay, and let's draw 4.3 centimeters. So about there. Okay, so that's 43 newtons. This angle is 25 degrees. Okay, the method we are using, by the way, is to parallel transport this vector to the head of the, so we transport the tail of the 43 newtons drag force to the head of the 70 newtons engine force, okay, and therefore the resultant force will be this one, okay. So this is what we are trying to do. So let's use a red color, okay, to connect. Okay, so that's the resultant force. Okay, so now let's measure it. So it's about 3.6, so 36 newtons. So I'm gonna write it here. So 36 newtons, and let's measure the angle. So remember, we go backwards from 180. So let's see. Wait, now it actually did it correctly because we are going in the other direction. So so let's see. 31 degrees. Okay, so 31 degrees is the angle. Okay, so I think the mark scheme is usually flexible with these values. So if you find 37 or 35 or even 38 newtons, it will be fine. Same with the angle. Okay, so this is part A. Let's move on. It awards 5 marks. Okay, so they value the ability of students to actually solve this kind of problems. Okay, let's move on to part B. Okay, part B is a long writing problem, and now comes another tip I didn't mention yet in this video. So in long writing problems, you get 6 marks. So you have to provide about 6 sentences describing the situation, verifying a result, whatever it is the question, okay? And whatever it is they are asking you in the question, excuse me. And if it awards 3 marks, it should be 3 sentences and so on and so forth. So a crane on a ship can lift the submarine out of the sea as shown. The submarine is initially completely underwater and at rest just below the surface. A cable from the crane is attached to the submarine so that the cable is vertical. The crane pulls on the cable. The submarine moves vertically upwards at a constant speed until the whole submarine is out of the water. Explain how the tension in the cable changes as the submarine moves from below the surface of the water to being completely out of the water. You should assume the drag force on the submarine is negligible. Okay, I mean, because the speed is low, I guess. Okay, so this is the sea and this is submarine. Okay, so if it's fully underwater, the forces are the weight, right? The upthrust and the tension from the cable. Okay, so if it's partially submerged, we still have the weight and the tension and a little bit of upthrust, right? And if it's fully out of the water, we only have the tension. Excuse me, I don't know why that happened. We only have the tension and the weight. Okay, so actually let's call this T prime and this T double prime because the tension changes as the submarine moves out of the water. Okay, now let's go use a clean page and explain all this. So while the submarine, okay, is fully submerged, okay, it experiences the weight, the upthrust, and t with with the tension being equal to the upthrust. Let me see. Sorry, the tension plus the upthrust is equal to the weight. So the tension is equal to the weight minus the upthrust. Okay. Since it moves at v equal to constant, right? This means a is 0 and t plus u is equal to the weight, which is what we just wrote. So excuse me for repeating it. Okay, so as the submarine starts to leave the water, okay, less of it is submerged. Okay. So the displaced volume reduces. Okay, which is what we see in this picture over here. The submerged volume reduces, so therefore the upthrust reduces. So thus the upthrust reduces. Okay. Thus T increases, right? And this is because in this situation, for example, we have T prime plus U equal to, actually it's going to be U prime, okay? So T prime is weight minus U prime, okay? And U prime is less than U, this U over there, okay? So upthrust reduces because part of the submarine gets out of the water, okay? So once the submarine is out of the water, the tension in the string is equal to the weight, and tension is maximum. Okay, so let's call this T double prime. Okay, and this is the situation over here. So the T double prime is equal to the weight. Okay, so that's the maximum tension. Okay, so this was question 18. Let's move on. Okay, question 19. Scientists launched a projectile from a mountain. The launch site was 2 kilometers above sea level. The projectile initially moved with a speed of 500 meters per second at an angle of 22 degrees to the horizontal. A ship was a horizontal distance of 15 kilometers from the launch site as shown. The projectile passed over the ship. This actually sounds terrifying. I don't know why. What kind of thing they were studying. I mean, if this is a real situation. So it sounds terrifying for the people in the ship, unless the ship was not manned, didn't have any people on it. So maybe it was an unmanned ship. Anyway, question A. Show that the projectile was vertically above the ship about 30 seconds after launch. You should ignore the effects of air resistance. Okay, let's do some preliminary calculations. So the initial velocity in the x direction is going to be 500 times the cosine of 22 degrees. So we are resolving the vectors pretty much. So we have ux, okay, and uy. Okay, so that's uy. Okay, so that's 463.6 meters per second, and uy is 500 sine 22 degrees. So that's 187.3 meters per second. Now let's go do part A. So vertically above, as it's stated, so vertically above the ship means the projectile covered 15 kilometers in the x direction. So we're going to use x. In the x direction, we have s is u times t plus 1/2 at squared, but there is no acceleration in the x direction. So x is ux times t, and ux is 463.6 meters per second times 30 seconds gives us 13.91 kilometers. Okay. So close to 15 kilometers. So the statement works. Okay. So yeah, I guess it will take about 32 seconds, I think, to be exactly at 15 kilometers, but okay, so that works. Okay, let's do part 2. Determine the height above sea level of the projectile as it passed over the ship. You should ignore the effects of air resistance. Okay, so in the y direction, we can again use S is u times t plus 1/2 at squared. So y, the height, is going to be uy, the initial velocity in the y direction, times t minus 1/2 gt squared. So this yields 187.3 times 30 seconds minus 9.81 over 2 times 30 squared for the second squared. So we get 1204.5 meters, but we are also 2 kilometers up. Okay, so but we are 2 kilometers from the sea. Okay, let's use a clean page. From the sea when we launch. So the total height, okay, is 2 kilometers plus 1.2 kilometers, so 3.2 kilometers. Okay, so this was part 2, and we're left with part B. Okay, part B. The scientists launched several more projectiles, which sounds even more terrifying. Okay, each projectile was launched at the same speed, but at a different angle to the horizontal. As the launch angle was increased, the horizontal distance traveled between landing in the sea increased to a maximum value and then decreased. Explain why the horizontal distance traveled reached a maximum value. You should consider the components of the initial velocity. So, as the launch angle increases, okay, the horizontal component, okay, of the velocity, which is u cosine theta, okay, decreases. Okay. At the same time, the vertical component, which is v sine theta, increases. Okay. So a larger uy means the projectile stays in the air for longer, before it lands. Okay, let's create a clean page. The horizontal distance though traveled, so the horizontal distance traveled, okay, depends is with a d, right? So depends on both vx and t. Okay, so these effects work against each other. Okay, so the distance reaches a maximum at some angle. Okay, and then it decreases rather than increase indefinitely. Okay, so this goes back to this part pretty much. So the horizontal distance is proportional to ux times t, right? So as the angle increases, ux decreases, okay? But t, the second component, depends on uy, okay? So these two effects kind of cancel each other. Okay, so this was question 19. Let's move on to question number 20. Before we move, remember when I said that in writing problems, the number of sentences you have to provide is proportional to the marks. So this is a 4-mark question, and we wrote 1, 2, 3, 4 points. Okay, so I hope this helps. Let's move on to the last question, which is 20. Okay, question 20. A student determined the terminal velocity of a metal sphere falling through a container of oil. The student released the sphere from rest in the oil, explaining why the sphere reached the terminal velocity. Okay, let's draw the forces. So initially outside the water is just the weight, the oil. And then inside the oil, we have the weight acting down, the upthrust, and the drag force. Okay, so these are not drawn to scale, by the way. Okay, now let's go use a clean page and write down what's going on. So initially, the sphere is at rest. Okay, so sigma f points downwards. Okay, and the weight is larger than the upthrust plus the drag force. Okay, the drag force, initially drag force is 0 since the velocity is 0. Okay, and the weight is larger than the upthrust. Okay, sphere accelerates downwards since sigma f is equal to ma. Okay, now since the drag is proportional to the velocity, as the velocity increases, the drag increases, and the upthrust is constant. Okay, it doesn't depend on the velocity. So eventually, the weight becomes equal to the drag force plus the upthrust. So the sum of all forces is 0. Thus, the acceleration is 0. So the sphere reaches a terminal velocity. Okay. B. The student measured the time taken for the sphere to fall through 0.45 meters of the oil at terminal velocity. Okay. Calculate the viscous drag force on the sphere. Assume the conditions for Stokes' law applied. The time taken is 7.3 seconds. The radius of the sphere is that. And the viscosity of the oil is also given. Okay, so the velocity is distance per time. So 0.45 meters over 7.3 seconds yields 0.062 meters per second. So the drag force, which is the Stokes force, is 6 pi times the radius of the sphere times the viscosity times the velocity. So we get 6 pi times 0.9 times 10 to the negative 3 times 2.1 times 10 to the negative 1, which is the viscosity times 0.062, and this yields 2.2 times 10 to the negative 4 newtons. Okay, and let's move to the next question. Okay, part 2. The student repeated the experiment using a second sphere with a greater diameter. The density of the second sphere was the same as the density of the original sphere. Okay, the temperature of the oil was the same, and then the conditions for Stokes' law applied. Explain how the time taken for the second sphere to fall through 0.45 meters at terminal velocity compares with the time taken for the original sphere. So, okay, the drag is proportional to the radius, so the new drag is larger. Okay, the weight is equal to rho times volume times g, so that's proportional to r to the cubed, right? And the upthrust is equal to the density of the liquid times the volume displaced times g, so it's also proportional to r cubed. Okay, so the upthrust and weight are increase more than the drag. Okay, so the ball will fall faster as we can actually write down the forces. So the weight minus drag is the weight minus the upthrust. So weight minus upthrust is equal to the drag force. Okay, so the weight is equal to the density of the sphere times g times 4/3 pi r cubed minus the density of the liquid times g times 4/3 pi r cubed. This is equal to 6 pi r times the viscosity times velocity. Okay, so if we delete this one of the r's, right, so we have r squared, we see immediately that v is proportional to r squared. So for a larger sphere, v terminal is larger. Okay, so this was Unit 1 from January 2025. Guys, please like and subscribe. Increasing the subscribers help the channel get exposure and get more famous and get more views and stuff like that. The channel is getting close to achieving a YouTube partnership, but I'm not there yet. So, and even if I do, it's not gonna make me a living yet. So please forward these videos to people that might find them useful. Let me know what you think about these videos in the comments. The next few videos might not be on past papers. I might actually upload some videos that are gonna be lecture-like, okay? And I also plan videos on research topics in physics and stuff like that, but you will see. Anyway, hope you enjoyed these videos and that they are useful. See you in the next one. Bye.